So we've learned about two important concepts, the cutoff probability and the error matrix. Let's learn how to do these things with R. Pretty straightforward. We'll take a look at them. Okay, so here's a data set that we have. And again, we've got income, education, state, class, and the probability. Okay, so obviously, all of these columns are coming from the test partition. These are our predictor attributes. That's the target attribute. And this probability has been generated by some model, right? As we already have discussed, a classification model first generates probabilities, and then we go ahead and use a cutoff probability to generate the actual class. Okay, so these are the model generated probabilities for each of the rows being a buyer. So the first row has a probability of 0.3 of being a buyer, and for example, this row has a probability of 0.75 of being a buyer, and so on. Okay, so that's the data set we have. Now let's learn how to apply the cutoff probability and generate the class with R. Okay, so here is a file that you can also use. I have posted it on Blackboard. Read.csv cutoff probability example.csv. Okay, so we're putting that into a data frame. Now this data is just the data that I showed you in the previous slide, this data. Okay, so assume that this is just the test partition alone, if that's what you want to look at it. So I'm saying I'm creating a variable called cutoff, and I'm putting the value 0.5 because 0.5 is the cutoff that I want to apply. And I'm saying that is our data set. Dat dollar model underscore pred underscore 5, right? So I'm creating a new column to store the model predictions. So that is why I call the new column as model underscore pred. And I said underscore 5 just to indicate that these are predictions with a cutoff of 0.5. Okay, there's no hard and fast rule that says how you're supposed to name them, but I just thought that this would conveniently tell us when the moment we look at the column name, we know, okay, this is a model prediction and it has been applied with a probability of 0.5. Okay, that's it. And how do I generate that? Obviously, you know that with a cutoff of 0.5, if any probability is less than 0.5, we are going to classify it as the negative class, right? Because all the probabilities are probability of being a buyer. And the higher that probability is, the more we want to classify them as a buyer, right? So if the probability is low, then we want to classify them as a non-buyer. So with a cutoff of 0.5, any probability value less than 0.5 is going to become a non-buyer. All other probabilities are going to become buyers, right? So we can achieve all of this by using the if-else function of R. Okay, this just works very much like the if function in Excel. So we say if-else dat dollar probability, right? That's the name of the column, right? If we go back to our previous slide, okay, so this is the column probability, right? So we are saying if else that dollar probability less than cutoff happens to be 0.5, then the result is non-buyer, otherwise the result is buyer. So comma, comma. So that's how the if else function works. If else, the first argument is the condition, that dollar probability less than cutoff. The second argument is what is the result of that expression if the condition happens to be true? And what is the result of the expression if the condition happens to be false? That's it. Okay. And the result, either non-buyer or buyer, goes into the column called dat dollar model underscore pred underscore 5. So if you do that, you see there's a new column. And this is the first one is classified as non-buyer because it's less than 0.5. Second is also non-buyer. Third is also non-buyer. Fourth is fifth. All of these are up to fourth. They're all non-buyers because they're less than 0.5. Here is the first value that is greater than 0.5. So it becomes a buyer, and so on and so on. As simple as that. Just use the if-else function and you're done. Very simple. Okay, so here I'm just showing you how to apply multiple cutoff probabilities. So for example, I say cutoff. I want to generate the predictions for different values of the cutoff for 0.33, 0.5, and 0.75. Okay, so I'm creating a vector called cutoff. C, you know that the C function is used to create a vector 0.33, 0.5, 0.75. And here I'm creating the column dat dollar model underscore pred underscore 33, that is for 0.33. If else dat dollar probability less than cutoff of 1, that's 0.33. Non-buyer, buyer. The next one is going to be less than cutoff of 2 and pred 5. Of course, the result in this case will be the same as what we saw earlier. And 75 is for 0.75, cutoff of 3. Okay. Of course, you could have put directly, instead of having a vector, you could have directly said 0.33, 0.5, 0.75. You could have done that. I'm just creating a vector and using that. So the result of all that will be that you will now have 3 columns. Model pred 5, model pred 33, and model pred 75. The order may be different because this model pred 5 came because I already executed it earlier. So that column came first. And these 2 columns have come later. So the order of columns, if you do it, would be different. You will get 3 first, 5 next, and 7 5 later if you do it in this order, right? Whereas if you did the earlier slide as well, if you did this first, then you will have it in the same order that I have it. Doesn't matter. Order doesn't really matter. Now that we have generated the predictions for 3 different cutoff values, and we could have done it for many more cutoff values actually, let's try and generate the error matrix for each of those cases. So let's see how we can use R to generate the error matrix. So I'm just saying cat cutoff equals 0.33. Cat is just a way to print something on the console, right? So that is, an error matrix is going to come up later. We just want to know what the error matrix corresponds to. So I just say cat cutoff equals 0.33. That just prints 0.3 cutoff equals 0.33 on the screen. And then we say table actual equals dat dollar class. Okay, so we are saying actual equals dat dollar class because dat dollar class, the column class, contains the actual status, actual class for each of the cases. Okay, and then I'm saying predicted equals dat dollar model pred 33. That is the model's prediction with a cutoff of 0.33, cutoff probability of 0.33, right? So we are just generating a table with the actual class and the predicted class. Okay, so this will generate the error matrix for us. It will generate this for us. Okay, it's going to say predicted buyer, non-buyer, actual buyer, non-buyer, and we're going to get 5 0, right? So if the cutoff is 0.33, then all the 5 buyers are going to be predicted as buyers. But since the cutoff is so low, 7 non-buyers will also be predicted as buyers, right? Because the cutoff for somebody being treated as a buyer is extremely low. So that's going to happen. And only 1 non-buyer is going to be correctly predicted as a non-buyer. Okay, you can verify this by actually looking at the data. So for example, if we go back here, right? So here you're saying model pred 33, right? Almost everybody is predicted as a buyer. There's only 1 person being predicted as a non-buyer, and that's a probability of 0.3. Okay, everybody else has a probability that's higher than 0.33 or 0.33 or more. So that's why this is happening. So this column result is what you're seeing here. Okay, now we can do the same thing for 0.5, cat cutoff 0.5, right? So this cat cutoff equals 0.33 is what resulted in printing this cutoff equals 0.33. And then we do the same thing, except that instead of model pred 33, we say model pred 5. So that generates this thing, right? So you now see that there are, since the cutoff to be accepted as a buyer is now higher, right? You see that there are fewer people, actual buyers, being accepted as buyers because the cutoff is now higher. Their probability was lower earlier, was lower than 0.5. So they are being classified as non-buyers. Similarly, more of non-buyers are being classified as non-buyers, right? That is because the cutoff is now slightly higher. So people who were earlier being classified as buyers are now being classified as non-buyers. Similarly, you do for 0.75 as well, and then you see the same result. Okay, so you see that in fact, as the cutoff goes higher and higher, the number of people being classified as buyers is reducing, 532. The number of people being classified as non-buyers is increasing, 1, 6, 7, etc., which is what we expect. So now comes the all-important question. Okay, given that if I choose a different cutoff probability, I get a different error matrix, right? So obviously my model performance depends very heavily on the cutoff probability. So the big question is, how do I choose the cutoff probability? And that is the subject matter of the next lesson.